Alright, in this video we're going to be talking about something called the superposition of vectors. Specifically, we're going to be adding electric field vectors today. So there's a general process for this, but before we start anything, we're going to need an arrangement of charges. I'm going to stick with what I've done in class and use blue for negative and red for positive. So we're going to put an electron right here, a proton right here, and something called an alpha particle up here, which has a charge of 2 protons. And then we need a location where we're going to measure the electric field, and we're going to have that be off here over to the side where that little black X is. We're also going to need some distances labeled here. So this distance from the proton to the electron is 2 centimeters. The distance from the electron to that X is going to be 1.2 centimeters. And the distance from the alpha particle to the electron is going to be 3.4 centimeters. And just to make things clear, I'm going to give each of these a name. I'm going to call the proton Q1. I'm going to call the electron Q2. And I'm going to call the alpha particle Q3. So the first thing to do in our process here is to draw our vectors. We should be able to figure out the directions just from what we know about the electric field. Let's go through the charges one at a time. Each charge will create an electric field at that point where the X is, where we're measuring the electric field. Electric fields from positive charges point away from the positive charge. So E1 from the proton will point in that direction. Electric fields from negative charges point towards the negative charge. So the electric field E2 will point in this direction. And last but not least, electric fields from positive charges again point away from the positive charge. Draw this dotted line here to help me make sure I get this drawn nice and straight. So there we have E3. So these are the directions of the 3 vectors that we're going to add up to do our superposition. And after we draw the vectors, the next step is to find the magnitude of each of our vectors. And we have a formula to find the magnitude of the electric field. That's E equals KQ divided by R squared. And this formula is just for the magnitude, so we're only going to plug magnitudes into this formula, and we already handled the direction before. So K is a constant that you'll need to know. That's 8.99 times 10 to the 9th. And the units of that are Newton meters squared per coulomb squared. We're also going to need to know the value of all of our charges. So Q1 is a proton, which has a charge of positive 1.6 times 10 to the negative 19th coulombs. Q2 is an electron, which has a charge of negative 1.6 times 10 to the negative 19th coulombs. We'll end up dropping that negative when we plug that in, but the charge technically is negative, so we may as well record it there. And Q3 is an alpha particle, which has the charge of 2 protons, so its charge will be 2 times the positive 1.6 times 10 to the negative 19th, which gives us 3.2 times 10 to the negative 19th coulombs. Again, positive. The last thing we're going to need for this formula is our values for R. R1's pretty easy to come by. R in this equation is how far is the point where you're measuring the electric field from the charge that's causing that electric field. So for the proton, that's 2 centimeters plus 1.2 centimeters, which is 3.2 centimeters. or in SI units, doing a quick conversion, 0.032 meters. R2 is labeled right on the diagram for us. That's 1.2 centimeters, which in SI units is 0.012 meters. For R3, we're going to have to do the Pythagorean theorem, and we can kind of see the triangle that we're going to use right here in orange or yellow or whatever color that happens to look like to you. But R3 will be the square root of 1.2 centimeters squared, putting the parentheses in there because we're squaring both the 1.2 and the centimeters, and 3.4 centimeters, quantity squared on the other side, which, after working through a little math, turns out to be 3.61 centimeters, or 0.0361 meters. Now we have all of the values we need, and we can plug and chug into our equation, making sure to drop any negative signs we have because we are just finding the magnitudes right now. So I'm going to trust you to plug these in yourself. But for E1, we get 1.40 times 10 to the negative 6th newtons per coulomb, which is the SI unit for the electric field. E2 turns out to be 9.99 times 10 to the negative 6th newtons per coulomb. And E3, plugging in the values that we need, turns out to be 2.21 times 10 to the negative 6th newtons per coulomb. So now we have the magnitudes and directions of each of our vectors, so we can move on to the next step, which is to choose a coordinate system and split these vectors into components. The coordinate system I'm going to use is going to have positive x to the right and positive y pointing upward. So, to kind of show you the chart that I use to keep track of these things, you have a column for x and a column for y, and you're going to add up E1, E2, and E3. And once you add those all up, you're going to get your total electric field, or E total. So let's go through these one at a time. First, we have E1. E1 is horizontal, it points straight to the right, so that is in the x direction. And whenever something's all the way in the x direction, that means its y component is 0, and the whole magnitude, that whole 1.40 times 10 to the negative 6th newtons per coulomb, goes into the x direction. And since E1 points to the right, and right is positive in our coordinate system, this is going to be a positive 1.4 times 10 to the negative 6th. Same story with E2, except E2 points to the left, so our y component is still 0, but now that 9.99 times 10 to the negative 6th newtons per coulomb has to be negative to account for that direction. So here's where we're bringing our direction into things and worrying about positives and negatives. Now E3 is diagonal, which means E3 is going to have both an x and a y component. And to figure out which is which and how to calculate those, we need to draw ourselves a triangle around E3. So there's our triangle, and that triangle will have an x component and a y component. And we're going to need an angle in that triangle. Let's pick this one. Now I could find that angle directly if I knew two other things about this triangle. I know the hypotenuse because I have the magnitude, but I don't know either of the components. That's what I'm trying to find. So trig and SOHCAHTOA won't help me here. So I'm going to have to resort to geometry. Now, the angle I've labeled as theta and this angle right here are vertical angles, or kitty corner angles. or catty corner, depending on what part of the country you're from. So if I can find this yellow-orange theta up here, I know that's the same as the theta down below. And to do that, I can use this bigger triangle that I've already drawn up here. Now, we actually technically have all three sides of this triangle because we know, or we already found, that this last side was 3.61 centimeters, but I'm still just going to use the tangent, and tangent of theta is opposite over adjacent. My opposite here is my 3.4 centimeters, and my adjacent is the 1.2 centimeters. So to solve for theta, we take the inverse tangent of both sides. So inverse tangent of 3.4 centimeters divided by 1.2 centimeters gives us theta is 70.6 degrees. So you'll notice that I didn't use SI units in my trigonometry there. I could have used the values in meters, I would have gotten the same angle, but since we have centimeters over centimeters, no matter what units I use, they'll cancel out. So I just decided that I would leave it in centimeters because it's shorter to write that way. But either way would work. So now we need to find the x component of E3, E3x, and the y component of E3, E3y. The x component, we should check the sign. The x component of E3 right here is going to be positive because it points to the right. And the component will be the magnitude, so that's 2.21 times 10 to the negative 6th newtons per coulomb. That whole thing times the cosine of theta, because the x component here is our adjacent side of the triangle, adjacent to this angle theta right here. And that works out to be positive 7.3 times 10 to the negative 7th newtons per coulomb. And that can go directly into our chart up here, positive 7.3 times 10 to the negative 7th newtons per coulomb. The y component, on the other hand, will still be the magnitude times a trig function. But if x was cosine, y has to be sine. And just to double check, E3y over here is, one, it's pointing down, so we need a negative sign because down is negative y. And it is the opposite component of this triangle because it does not touch the angle theta. And opposite goes with sine. And then that gives us a value of, where is it? There it is. Negative 2.08 times 10 to the negative 6th newtons per coulomb. And that can also go right in our table here. So now step 3 is complete. We've chosen a coordinate system and we have split all of our vectors into components and put them into our table. Now we need to add up the x and y columns separately to get the x and y components of our total electric field vector. The y component's easy because we only have one thing over there, negative 2.08 times 10 to the negative 6 newtons per coulomb again. And in the x direction, we can add all of those up, and we get, let's see, negative 7.86. Again, times 10 to the negative 6th newtons per coulomb. Now we have the x and y components of our total electric field vector. And of the 4 things you can know about any vector, the x component, the y component, the direction, and the magnitude, we now know 2. And when you know 2 of those 4 things, you can figure out the other 2 using trig and SOHCAHTOA. So, Now to find the magnitude of E total, we can use the Pythagorean theorem. So that's the square root of the x component, this 7.86 times 10 to the negative 6 newtons per coulomb. Quantity squared, make sure you get that negative inside the parentheses there, plus negative 2.08, again, times 10 to the negative 6th newtons per coulomb, quantity squared. And that turns out to be 8.13 times 10 to the negative 6th newtons per coulomb. And that is the magnitude of our total electric field. So that is E total. But we're not done just yet. We're going to need to find the direction of this electric field. So to do that, I recommend actually drawing your vector here. So when I say draw the vector, I mean pick a starting point and then draw your x and y components paying attention to the signs. So the x component here is negative, so we should draw that 7.86 times 10 to the negative 6th pointing to the left, newtons per coulomb. And then from there, our y component is also negative, so not at all to scale. My y component does point downward, and it has a value of 2.08 times 10 to the negative 6th, again, newtons per coulomb. And that means our total electric field vector will point in this direction. So this is E total. And hopefully this gives you an idea of what we're doing next. We are going to find an angle in this triangle. I like to find the angle at the tail of the vector, and I'm going to call it phi so that we can keep it straight from our other angle theta. Now we also have opposite, adjacent, and hypotenuse here, but again, I'm going to use tangent. So tangent of that angle phi is going to be opposite, so 2.08 times 10 to the negative 6 times 10 to the negative 6th newtons per coulomb divided by the adjacent, oops, that should be negative up there, 7.86 times 10 to the negative 6th newtons per coulomb. You might notice that I've dropped my negative signs here. It's because we've already accounted for the negatives when we drew our little triangle for E total, and the direction will come back in a little later as well. So again, we can take an inverse tangent of everything we have on the right side over here to find our direction. So I've kind of run out of room here, so I'm going to drop the units just for this step and drop the 10 to the negative 6th because it would cancel out anyway. And that gives us an angle of, let's check and see what my notes say, 14.8 degrees. Now that's not everything we need because every angle needs a reference point. You could say something like, well, our reference could be the negative x-axis, and we have gone counterclockwise from there. So we could say counterclockwise from negative x. Or, as I prefer to do, we can use our cardinal directions, north, south, east, and west. So this angle starts off measured from the east, and you go south from there. Or sorry, from the west, and you go south from there. So this is south of west. And that is our direction. The second direction in there is your reference line. So the angle is measured between E total and west. So west is our reference line, and then our angle goes south from there. So this is the entire problem of finding the total electric field. Now we have the magnitude and the direction. So I'm going to create myself a little space at the bottom here and ask a further question. What force would an electron feel if I put it at the location where we just calculated the electric field? So you might think, Dr. Mikula, that's not nearly enough space for this problem. But we don't have to do a whole superposition problem over again, because we know that the force, specifically the Coulomb force, and the electric field are related to each other by the formula F equals QE. So we've already done all the work of finding the electric field, and that allows us to use this simpler formula down here. So the force here is going to be the charge that we put there, the test charge, which is this electron. And electrons have a charge of negative 1.6 times 10 to the negative 19th coulombs. And I'm keeping the negative because this is a vector equation, so that will have implications for the direction, times the value of the electric field at 8.13 times 10 to the negative 6th newtons per coulomb. And the electric field originally had a direction, and that's part of the electric field. So I'm just going to put a little at 14.8 degrees south of west. So when we multiply just the magnitudes together, just those numbers, we get 1.30 times 10 to the negative 24th newtons per coulomb times coulomb gives us newtons. Or we could just say we've been working in SI units this whole time, so it better come out in an SI unit. And then we're left with a couple things we might not really know how to handle. We've got this negative sign and this direction. So the negative of a vector means that vector points the opposite direction. So because our charge is negative, we expect the force and the electric field to point in exactly opposite directions. So what that means is our direction here is still going to be 14.8 degrees, but that negative flips that south and west to north of east. So on our little diagram, or let's make a little diagram down here, the electric field, this is west, and our angle was measured south from west, so started at west and we went south from there. If we want to find the exact opposite of that, then our reference line is east, and from east we go north of east. But you'll notice it's the same angle. So this is now our answer for our force. 1.30 times 10 to the negative 24th newtons in a direction 1.48 degrees north of east. So a much shorter calculation now that we've done all the work of the electric field. And we could easily do another calculation here if we said, well, what if I put a proton there instead? What if I put an oxide ion there instead? What if I put an alpha particle instead? Each one of those problems would only take as much time and space as this force calculation we did in the bottom corner here. We wouldn't have to do it all again because the electric field is most of the force. The only thing that's missing is the test charge that we put there. So we could always come back to this equation right here and use that equation with the electric field we've already calculated. One small note, if you're doing south of west east of north, things like that. You just flip both of them. South becomes north, west becomes east. If you're doing the counterclockwise from negative x stuff, you keep the counterclockwise as it was, but you just flip the negative x to a positive x. So over here on our diagram below, west was our negative x-axis, and we went counterclockwise from there. East, on the other hand, is our positive x-axis, and we also went counterclockwise from there. So just be careful that it's a slightly different process of reversing your direction depending on how you do it. That should be everything for this problem. Thanks for watching, and you can expect to see superposition problems plenty of other times throughout this term, but this is a great example, and I can really give you any arrangement of charges as long as you can find the distances and the angles with the values that I give you and the values for the charge. You should be able to work through this process. It does require a bit of geometry at points and clever thinking, like we saw with this yellowish-orange section before. And calculating your magnitude is not the end of the problem. We then have to find our direction with a reference. So hopefully this helps, and I will see you all in class on Friday. And just in case, I'm going to write myself a little copyright here. Have a good day, and I will see you all tomorrow.